Okay, so now we're moving on to section 11.5, which is all about lines and planes in space. So when we talk about lines, one of the first things that usually pops into our minds is our good old friend y equals mx plus b, where b is the y-intercept and m is the slope of that line. And that's perfect if we're dealing with lines in two-dimensional space. However, when we're dealing with lines in 3 space, we lose kind of the meaning of slope. Because, yeah, maybe the line is increasing. Maybe that means for us that z is increasing, getting larger. But when? As x is increasing and y is increasing? As x is increasing and y is decreasing? What does that mean in 3-dimensional space? So slope doesn't really hack it in 3D. What we're going to have to do instead is describe this line using a direction vector. Okay, so here's what I mean by that. We are going to let L be the line in R3 passing through the point P, x1, y1, z1, okay? And then we'll give it direction by saying it's parallel to some vector v. Okay, and we'll say that vector is A, B, C. All right, so here V is the direction vector for the line L. So V is the direction vector for line L. And A, B, C are the direction numbers. And that is very analogous to the slope. This is going to be telling us how much does this line change from point P to another point in the x direction, y direction, and z direction. So it's talking about all 3 of the directions in one go. And we have a couple of different ways of describing this line using some nice equations. So the first thing we're going to do is use parametric equations. So parametric equations of a line in R3. Okay. So our parametric equations of a line in R3 are going to be defined by some parameter. So we're going to use parameter t to define x, y, and z. Okay? So if we have line L passing through point P, which is given by x1, y1, z1, and parallel to vector v, which is ABC, then what we're going to do is we're going to use some parameter, say t, and we're going to begin at x1. Then we are going to add in the x direction the x component times t, whatever that parameter is that we've chosen to use, okay? Because A is telling us how far we're moving in the x direction, B is how far we're moving in the y direction, C is how far we're moving in the z direction, okay? So here are the parametric equations. X is equal to x1 plus A times t, y is y1 plus B times t, and z is z1 plus c times t. Now, I don't know who decided that z and c should be paired up, but they had absolutely no respect for the difficulty of keeping those things straight while we're trying to say them. Okay, so these are the parametric equations of a line in space. Now, notice that the t in these is all the same t. So it's the same t in all 3 parametric equations. Okay, so what we can do is we can solve all 3 of those equations for t. And then what we end up with is t is equal to x minus x1 over a. T is equal to y minus y1 over b. and t is equal to z minus z1 over c. Well, since they're all equal to t, they're all equal to each other. So that implies that x minus x1 over a is equal to y minus y1 over b is equal to z minus z1 over c. That right there is what's known as the symmetric equations of a line. The symmetric equation of a line in R3. Okay. Make sure you've got that there. So you can be asked for the parametric equations or you can be asked for the symmetric equation. It doesn't matter which one you've got, because if you've got one, you've got the others. So let's do an example where we have to actually find those equations. So example, find the parametric and symmetric equations of the line passing through point 3, negative 2, 6, and parallel to vector v equal to negative 1, 4, and 5. Okay, so we have our point and we have our direction vector, which contains our direction numbers. So let's go ahead and set up our equations really quickly. So the parametric equations are x equal to 3 plus negative 1, really? Negative 1 times t. Y is equal to negative 2, because that's where we're starting. That comes from the point. Negative 2 plus the direction number 4 times t. And then z is equal to 6 plus 5 times t. Okay, so there are our direction, our parametric equations. So just to clear that up, 3 minus t, negative 2 plus 4t, and 6 plus 5t. Okay, so if you need to find a point on this line, x, y, z point, we can find that by choosing a t, plugging that t into each of these, getting the x, y, and z values for another point on the line. Okay, and once we have these, it's a simple matter to solve for t and get the symmetric equations. So let me grab another color here. Okay, so the x here, we've got x minus 3 is equal to negative t, so that's x minus 3 divided by negative 1. For y, it's y plus 2 divided by 4. And for z, that's going to be z minus 6 divided by 5. So that these each come from solving each of the above equations for t, and then setting those things equal to each other. We could simplify the left-hand, the x side of this equation here a little bit, making that negative x plus 3, but it is not necessary for me. Like, I'm not going to ask you to do that. If you left it just the way you had it at the beginning, I'm perfectly fine with that. All right. So something to keep in mind when we're looking for these equations is that these equations are not unique. They're not unique. There are an infinite number of vectors that would be parallel to this line, right? So these are not unique representations. So your answer may differ from your neighbor's answer, from another student's answer, whatever, and that's okay. It can definitely happen and still be accurate. All right, so let's do another example, except this time we're not going to be given the parallel vector or the direction vector. This time we're just going to be given 2 points on the line. Okay, so example, find the parametric and symmetric equations of the line passing through the points negative 2, 1, 0, and 1, 3, 5. Okay? Well, if we're going to do this, we need a direction vector, right? So let's call this my point P and call this my point Q. So L is the line going through PQ. Okay. Okay, I put arrows on both ends because it is a line. So I need a vector parallel to this line. Well, the vector between P and Q is parallel to this line. So that's going to be, let's see, 1 minus negative 2, 3 minus 1, 5 minus 0. So that is 3, 2, 5. Okay, so now we have a direction vector with direction numbers. Now you might have chosen to do this a different way. Maybe you wanted V to be equal to QP. That's perfectly okay. We will get different numbers, and when we set up our equations, we might get different equations. As long as it's representing the same line, it doesn't matter. Okay, so I am going to choose to begin building my parametric equations from point P. Okay, so I'm going to let x1, y1, z1 be equal to negative 2, 1, 0. Does it matter? Absolutely not. Does not matter. I could use Q for this. I could find a third point by adding vector V to P or Q. Well, if I add it to V, I'm going to get Q. But I could add it to Q and get another point, or subtract it from P to get another point on the line. But I'm going to go ahead and use this. So my parametric equations are x equal to negative 2 plus 3t. Okay, so just to remind you, the 3 is the direction number. We multiply that by whatever the parameter is, in this case t, and then we add that to the original point, our starting point. Okay, y is equal to 1 plus 2t, and z is equal to 0 plus 5t. Okay, so we have x equal to negative 2 plus 3t, y equal to 1 plus 2t, and z equal to 5t. So there's our parametric equations. That is the parametric equations of this particular line in space. So again, once we have this, it's very simple to come up with the symmetric equations. Solve each of these for t and then set them equal to each other. So we have x plus 2 over 3 is equal to y minus 1 over 2 is equal to z over 5. There we have it. So again, I've just solved each of the equations above, x, y, and z here, the parametric equations, solved those for t. It's the same t, so we just set those equal to each other. And there we have it. Okay. All right, so now we're going to talk about planes in space. All right, so to find the equations for a line, write that down, to find the equations for a line in R3, we need a direction vector parallel to that line. Okay, so for lines, we need parallel vectors. However, to find the equation of a plane in space, we need exactly the opposite. We need a direction vector that is perpendicular to the plane. Okay, this vector is called the normal vector. Okay, go to the plane. This vector is called the normal vector. Okay, so for a plane, we need a perpendicular vector, also known as a normal vector. And we typically denote this vector just as n, denoted the n vector, right? The normal vector. Okay, so how we're going to come up with this equation is by using the property of the dot product that says if two vectors are perpendicular to one another, then their dot product is equal to 0. Okay, so suppose I have got a vector PQ in the plane. So if PQ is a vector in the plane, and n is normal to the plane, then n dotted with PQ is going to give us 0. They're perpendicular to one another, so their dot product is going to be equal to 0, right? So, depending on what points P and Q are and depending on what the vector n is, we can just run the dot product and find whatever this happens to be. Okay, so we're going to let the normal vector be ABC. Okay, that's what we're going to call it. And we're going to let P be a specific point in the plane, x1, y1, z1. And we're going to let Q be any point in the plane, x, y, z. Okay, I just need one point in the plane. After that, we need Q to be free to be any point because we want to collectively represent all possible points in this plane, right? So PQ then is equal to it's a vector, x minus x1, y minus y1, z minus z1. Okay, and now we're going to dot in times PQ. We're going to dot in with PQ. So that's going to be A, B, C dotted with x minus x1, y minus y1, z minus z1. Okay, so if we do the dot product, what we are going to get is A times x minus x1 plus B times y minus y1 plus there we go, C times Z minus Z1. And because these are perpendicular, we know that this is equal to 0. And that, my friends, is the standard form of the equation of a plane in space. Standard form of an equation of a plane in space, R3. Okay, if we distribute and collect like terms, call the constant term something like D just to represent the constant, what we will end up with is what's known as the general form. So that's AX plus BY plus CZ plus D, which is just representative of all of the constants, equal to 0. So that's general form. But of course, standard form is the most useful because standard form it has all the pertinent information just staring at us. It has the direction vectors from the normal vector, and it has the point x1, y1, z1 sitting right there inside of it. So this is very, very useful, and we can find equations of planes in three-dimensional space. So let's go ahead and do that now with an example. Let's find the standard form of the equation of the plane containing the points, okay, 2, 1, 1, 0, 4, 1, and negative 2, 1, 4. Okay, so we have a plane. We do need 3 points to nail down a plane. Because any 2 points are collinear, you throw out one more point that's not collinear, and we have a plane. All right, so we do need 3 points for that. And we are going to find the standard form of the equation for this particular plane. So how do we do that? Well, I'm going to need a couple of things. First of all, I need a point in the plane. Well, that's easy. I've got 3 of them. I can pick any one of them. Second, I'm going to need a normal vector. So we're going to have to find... we need to find a normal vector. Doesn't matter what normal vector, just so long as it's perpendicular to the plane. So how are we going to do that? Well, we've got 3 points. And if I've got 3 points, I've got at least 3 vectors. I have at least 2 vectors. I've got 3 vectors. So we have, I'm going to give these points names. I'm going to call this one P, call this one Q, call this one R. All right. If I have 2 vectors lying in a plane and I cross those 2 vectors, we're going to get a normal vector. So let me write that down. So we obtain a normal vector by crossing any 2 vectors in the plane. Okay. So I need a couple of vectors in the plane. So let's do PQ. That's going to be 0 minus 2, 4 minus 1, and 1 minus 1. And let's do QR. So that'll be negative 2 minus 0, 1 minus 4, and 4 minus 1. Okay. Now, a moment ago I said we have 3 vectors. We actually have more than that, right? Because we could do them in different directions. We could do QR or RQ, PQ or QP. We could do PR or RP. So that doesn't matter for this purpose. We need any normal vector. Doesn't matter which direction it's pointing out of the plane, so long as it's pointing straight out of the plane. Okay, so these are going to be the vectors negative 2, 3, 0, and negative 2, negative 3, 3. Okay, so we're going to go ahead and cross those. So PQ crossed with QR. That's going to be the determinant of, right? So we have I, J, and K. And then PQ is negative 2, 3, 0. QR is negative 2, negative 3, 3. So that is going to be in the I direction, so that you see it again here. I times the determinant of 3, 0, negative 3, 3, minus J times the determinant of negative 2, 0, negative 2, 3, plus K times the determinant of negative 2, 3, negative 2, negative 3. So that is going to be I times 9 minus 0 minus J times negative 6 minus 0 plus K times positive 6 minus negative 6. So that's going to be in component form 9, negative, negative 6, so positive 6 and 12. Okay, so there is a vector normal to the plane. It is not unique. There are gobs and gobs and gobs of vectors normal to the plane. I just need one of them. This cross product gives me one of those. Okay, so now I have got my normal vector. So I'm going to put a circle around it so I don't lose it. And I'm going to choose any point from the plane. So I'm going to come back up here, and it doesn't matter. I'm P. P looks good. Any point in the plane, doesn't matter which one. So my point, x1, y1, z1, is going to be P, which is 2, 1, 1. Okay, so I've got my ABC for my normal vector. I've got my x1, y1, z1. I'm ready to write down the standard form of the equation here. So we have got 9 times x minus x1 is 2, plus b, which is 6, times y minus y1, which is 1, plus c, which is 12, times z minus z1, which is 1, and all that is equal to 0. There is the standard form. Now, for working with this, general form is pretty handy, so we might as well go ahead and find it since we're here. So this is 9x minus 18 plus 6y minus 6 plus 12z minus 12 equal to 0. So that's going to be 9x plus 6y plus 12z, and then we have negative 18 minus 6 is negative 24, minus 12 would be negative 36, equal to 0. And there we have it. If we wanted, we could simplify further. Everything has a 3 in it, so we could simplify by dividing out a 3. So I'll write or 3x plus 2y plus 4z minus 12 is equal to 0. Okay, so these are identical. They're identical. So I would accept any one of these. So this is your standard form. Go ahead and label it standard. Standard. And this is, of course, general. And if I asked you for standard, I would accept that. If I asked you for general, either of these would do. So how do we check our work? Well, we can check our work by plugging in all 3 points into the equation to make sure it comes out correctly. We don't really need to plug in 2, 1, 1, since that's the one we use to build it. And if we plug in 2, 1, 1, obviously we get 0. But we could go ahead and plug in 0, 4, 1 and negative 2, 1, 4 just to verify. So I'll let you do that on your own if you're interested. All right, so planes in space behave very much like lines in 2 dimensions behave. So if we have 2 planes in R3, those planes can either be parallel or they can intersect. And if 2 planes intersect, they intersect along a line. All right, so let's talk about that a little bit. So planes, let's go back to white. There we go. Planes in space are either parallel or they intersect along a line. All right. Okay, so the angle between two planes, we have a formula for that, but just to be aware, it's always going to be the acute angle between the planes. So for theta, let me back that train up. For theta between 0 and pi over 2, okay, the angle theta between the planes is given by cosine of theta equal to the absolute value of the dot product of the normal vectors n1 dotted with n2 divided by the magnitude of n1 times the magnitude of n2. Okay, so that is where n1 is normal to the first plane and n2 is normal to the second plane. Okay. All right. Now, if n1 dotted with n2 is 0, we know that they're perpendicular to each other. These two planes are going to be perpendicular to each other. The planes are perpendicular. Okay. And if n1 is a scalar multiple of n2, then we know the planes are parallel. All right, so if we have two planes intersecting, it makes sense that the next question would be, well, what is that line of intersection? So let's do an example so that you can see kind of how we find that line of intersection. So we'll take this opportunity to find both the angle and the line of intersection. So example, find the angle between and the line of intersection of the planes. Okay, so here they are. 6x minus 3y plus z equal to 5, and negative x plus y plus 5z equal to 5. All right, so step one, let's go ahead and find that angle. Let's find the angle between the planes. So that shouldn't be a big deal. We have a lovely formula. So cosine of theta is equal to n1 dotted with n2, absolute value, divided by the magnitude of n1 times the magnitude of n2. Okay. All right, so only thing we have to do is come up with n1 and n2. So that is not going to be difficult to do. We have two planes here. So I'm going to call this one equation 1, or plane 1, and this one I will call plane 2. All right. So n1 is the normal vector to plane 1, n2 is the normal vector to plane 2. Well, these are written in general form. And so the components of the normal vectors are just the coefficients of x, y, and z. So we have n1 is equal to 6, negative 3, 1. n2 is equal to negative 1, 1, and 5. All right, so there's our normal vectors. So we dot those, n1 dotted with n2. That's going to be equal to 6 times negative 1 plus negative 3 times 1 plus 1 times 5. So that's negative 6 minus 3 plus 5, which would be negative 4. We want the absolute value of that. So I'm going to come back in with another color. Let's find that absolute value. So that's going to be equal to 4. So the numerator for our cosine is 4. So we have cosine of theta equal to 4 over. So now we need to know what are the magnitudes of n1 and n2. Well, the magnitude is the square root of each component squared and added together. So 6 squared plus negative 3 squared plus 1 squared times the square root of, now into, negative 1 squared plus 1 squared plus 5 squared. So this is 4 over the square root of 36 plus 9 plus 1 times the square root of 1 plus 1 plus 5. Okay, so that is 4 over the square root of 46 times the square root of 5, 6, 7. No, did I miss something? I forgot to square the 5. Did you guys see that? Did you catch that mistake I made there? Got to square that 5, so it's 25. There we go. So 25 plus 2 would be 27. Now 46 times 27, getting the calculator here, is 1242. So this is 4 over the square root of 1242, which is approximately equal to, let's see here, square root of 1242. Which is, if I can type in my calculator, approximately 0.11350087, etc. And then I need to solve that for theta. So cosine of theta is approximately equal to 0.11350087. So theta is the inverse cosine of this decimal. Okay, so that makes theta approximately equal to the inverse cosine of that answer. Now, I did not retype that. I didn't round it. I just left it in the calculator to find it. And we get that theta is approximately equal to 1.4571. Now, in a calculus course, it is always best practice to keep your angles in radian measure. In an application problem where we need to find degrees, that's great. We can do that. We can find that degree. However, in general, we want our angles to be in radians because many of our formulas do not work unless theta is in radians. So we want to make sure that that's the case. All right, so we have 1.4571 as our angle. And that is less than pi over 2. If you calculate pi over 2, it comes out to be approximately 1.57. So this is an acute angle less than pi over 2. So we're good to go. There's our angle. All right, so now we have to find the equation, the parametric equations, rather, of the line of intersection. So how in the world are we going to find that? So line of intersection. I'm going to rewrite the equations for the planes here just so that we have them in front of us again. So the first one was 6x minus 3y plus z equal to 5. The second one was negative x plus y plus 5z. That is the worst plus. Let's try again. Equal to 5. All right. And the normal vectors then in 1 was 6, negative 3, 1. In 2 was negative 1, 1, 5. Okay, and we have to figure out what is the line of intersection. Well, in order to give the parametric representation of that line, we have to have two things. We have to have a point and we have to have a direction vector. So let me write that down. So we need a point on the line and a direction vector parallel to the line. Parallel to the line. Okay, so first thing I'm going to do is I'm going to find that vector parallel to the line. And the way we're going to find that is by finding the cross product of the normal vectors. Because if something is orthogonal to the plane, if a vector is orthogonal to the plane, it stands to reason then that another vector orthogonal to the normal vector must be parallel to the plane. So if I find a vector that is orthogonal to both in 1 and in 2, that vector will be parallel to both plane 1 and plane 2. So that's what we're going to do. So the parallel vector is the cross product in 1 crossed within 2. Okay? All right, so let's go ahead and find that really quickly. So in 1 crossed within 2 is going to be equal to the determinant I, j, k. In 1, 6, negative 3, 1. In 2 is negative 1, 1, 5. And again, this just has to be parallel to the line. It doesn't have to be in a specific direction so long as it's parallel. So we could cross into within one and it wouldn't matter. We would still be able to find a valid representation of the line. Okay, so this is going to be I times the determinant negative 3, 1, 1, 5 minus j, don't forget that sign, times the determinant 6, 1, negative 1, 5 plus k times the determinant of 6, negative 3, negative 1, 1. So that's going to be in vector form. That'll be negative 15 minus 1 is negative 16, negative 30 minus negative 1, which is 31, and then positive 6 minus 3, which is 3. So we have negative 16, negative 31, and 3. So that is our direction vector parallel to the line of intersection. Now the next thing we need is a point. So to find the point, we're going to have to use the equations of the planes, and we're going to have to narrow it down a little bit. What we're going to do is we're going to create a system of equations in two variables. So how do we do that? Well, what we're going to do is we're going to choose a value for one of the variables, right? So let's choose a value. 0 is always nice. For one variable, and then we'll solve the remaining system of equations to find the other two variables. Okay. All right, so back to our equations of these planes. It was 6x minus 3y plus z minus 5 equal to 0 if I pull that negative 5 over. And, oh, I don't even need to do that, do I? Let's just leave the 5 on the other side of the equal sign. There we go. Don't need to mix things up just yet. And the second one was negative x plus y plus 5z equal to 5. All right, so might as well just make z equal to 0. I chose a variable, and I'm going to plug that in. So I'm going to choose, and it's completely arbitrary which one I choose, z, and I'm going to set that equal to 0. So then what I have is 6x minus 3y is equal to 5, and negative x plus y is equal to 5. Now I have a system of two equations in two variables that I can solve. So let's find the solution. So let's see here. If I multiply, let's see, 6x minus 3y is equal to 5, I can multiply this equation, the second equation, by 6 and eliminate the x. I can do that. So that'll be negative 6x plus 6y is equal to 30. Let's add those up. So I'm going to get 3y is equal to 35, y is equal to 35 thirds. So don't let that throw you. It's okay. Fractions happen. It's not a big deal. Fractions are okay. And now let's go back and find the x value. I think it would be easier to eliminate the y instead of doing substitution. So let's do that. So we've got, this time I'm going to multiply it by 3 to do my elimination. So I've got 6x minus 3y is equal to 5, and negative 3x plus 3y is equal to 15. Add them up, eliminate the y's, we get 3x is equal to 20, x is equal to 20 thirds. So our solution then, or I should say our solution, a point on the line of intersection is 20 thirds, 35 thirds, 0. So there's our point. So now we have our directional vector parallel to the line and a point on the line. It's a simple matter now to come up with those parametric equations. Okay, so there's my point. I'm going to go back up and find the vector. Where'd the vector go? There it is. So here's our vector. Negative 16, negative 31, 3. Let's write it down. And I can set up the parametric equations of the line. So x is equal to 20 thirds minus 16t. Remember, so this is my ABC here. I'm sorry, this is my x1, y1, z1, and this is the A, B, and C, which are our directions in those different, in the x direction, y direction, and z direction. They're going to give us the magnitude of the change in that direction. So there's x. Y is equal to 35 over 3 minus 31t, and then z is equal to 0 plus 1t, no, 3t, sorry, I got 3, there it is, plus 3t. Okay, so that is x equal to 20 thirds minus 16t, y equal to 35 thirds minus 31t, and z equal to 3t. Boom, there we go. And again, this is not unique. You could have come up with totally different points. If you had chosen a different variable to make 0, you would have found something different, and that's perfectly okay. We do not all have to match exactly. What's important is that these parametric equations will yield the same points for every point on the line. Okay, so this video has gotten super long. This is a very beefy section. So I'm going to go ahead and stop this one here, and I'll do a part 2 for this section. So stay tuned for part 2 of section 11.5.